Welcome back, everybody. Let's continue with the physical layer. It's always the good old approach that I told you, data independence. So I first teach the logical aspects, how to use it and so on, and then how it's implemented. So now is how Spark is implemented. So I told you that some of the transformations or actions are spaghetti-y and some others are not. So I'm going to start with those that are not spaghetti-y. This one, you agree with me, is not spaghetti-y, right? There's just vertical lines nicely going vertically. So there is no spaghetti in there. So how can you efficiently map? So that could be a map or a filter or whatever you want. How do we efficiently execute that in a cluster? We do it in, it's written on the slide, in parallel, right? So if I put these lines right here, these vertical lines, I can basically chunk or split or partition or many other words for that, my input. That gives me tasks, right? So I have one task, second task, third task, fourth task, and I can do it in parallel, for example, on 4 different machines. Or I can have more tasks than machine, and then some machines take multiple tasks, right? But if you look at these slides, you will agree that I can execute a non-spaghetti transformation in parallel by creating these tasks, right? Who agrees with that? Right? It's pretty natural. By default, if my RDD is directly freshly coming from HDFS, like I just freshly created an RDD by reading it from HDFS, then it's the same idea as in MapReduce, is that the way to chunk my input, if it's on HDFS, is that's one block, one block, one block, one block, right? Same idea as in MapReduce, if that directly comes from HDFS. All right. And then you have on the top the logical layer. That's what the user sees. They just see an RDD that is transformed in another RDD, logical layer. But now if you look at the machines on the data center and what's going on, physically, we have partitioned it into 4 tasks, this transformation, and the map function or the filter function or the sample function or whatever you do in a non-spaghetti way is going to be done in parallel on the machines, right? Logical on top, physical at the bottom. Concretely, imagine I have more tasks than 4. So here I took an example with 11 tasks and 4 slots. Remember the tasks, the slots, and so on. The slots are basically the CPUs, if you want, and the CPU cores, and the tasks correspond to the splits, the chunks. So in that case, I have 11 tasks executed on 4 different processes or threads. I'll go more precise in that very soon. Why does executor 4, slot 4, have more tasks than the other? Just because it was faster in handling the first ones, right? It's first come, first served. Whenever an executor is done with a task, it just requests a new task. The faster it is, the more tasks it gets. And executors 1 and 3 were slower, so they took less tasks, right? It's dynamic. You notice this new word, executor, that is just a Spark word that corresponds to the slots, more or less. I'll come back to that. So executor, that word didn't exist in MapReduce, but now we have it in Spark. Executor, 1, 2, 3, 4. So normally you're with me on that, right? That is similar to MapReduce. Now, there is a little thing, is that, in fact, these executors, they correspond to yarn containers. Remember that a yarn container is a couple of cores and a bunch of memory, right? So imagine that I take 2 containers in yarn that have 2 CPU cores and, let's say, 10 gigabytes of memory. Because there are multiple cores in every container, like this container right here has 2 cores, then do you see that it can handle 2 series of tasks in parallel, right? Because each core, you know, that's the purpose of the cores in the machine. It's to do things in parallel. So on one of its cores, it's going to take care of a few tasks, and another one of its cores is going to take care of other tasks. So in fact, this is why I was saying an executor is not exactly a slot. It's the cores that correspond to the slots, right, in the executor. But these two cores share the same memory, right? So whatever memory they use, it's shared in here. It's more efficient, gives a bit of flexibility because it might be that this core needs more memory and this one needs less memory, and so it's a bit shared, that's a bit more efficient, right? Likewise, we have here two other cores, so two different slots, and the shared memory. So we have one executor, one yarn container, one yarn container, okay? So we still have this idea of slots and tasks, but now what's new is the fact that these slots are going to have some shared memory in here. All right. Now, slightly more complex. What if I have something I do not have in MapReduce? What if I have multiple transformations, one after each other? And by the way, I forgot to say, because somebody asked on Zoom, I'm computing things here because I'm assuming that somewhere down there, somebody actually called an action, right? That's the assumption. That's why we're computing things, right? That there's an assumption. Of course, if nobody calls an action down there, nothing would actually happen. So I'm assuming somebody calls an action down there. So we have, in that case, three transformations, right? Two intermediate RDDs, an input RDD, and an RDD that comes out of the third transformation. I'm furthermore assuming that these transformations are non-spaghetti, right? There's no spaghetti, there's no shuffling, they just can be done in parallel. Very naively, you might think, okay, why don't we throw machines at the problem? And we do it in parallel in this way, right? That we have the first transformation on a couple of slots, the second transformation on a couple of other slots, and the third transformation on a couple of other slots. Does anybody see how inefficient this is? It's inefficient because it uses more machines than we need. It's inefficient because you see that some of the data gets shipped across machines. So is there any way, do you see any way that we could use less machines and we avoid sending the data over the cables between machines? Does anybody see that? Again, I'm assuming there is no spaghetti. It's one click away. I think the next slide probably has this, but I wanted to give you a chance if you see that. On Zoom, anybody see how to improve the efficiency here? If I show you, you're going to be like, ah, yes. Yeah. And indeed, this is how. Because it's non-spaghetti, so we just keep using the same slots, the same machines. They just apply the map or filter or whatever in sequence on the same data that they already have. So what happens is that this is my input RDD, right? This is my output RDD. And these are my two intermediate RDDs, right? Now, let me explain to you what's happening. First, do you agree we don't really care about these? These are just intermediate things that are in the middle. We don't actually care about this. What we do care about is this, right? Because this we might use somewhere else. So these are intermediate results that we don't care about preserving or keeping or whatever. So what's going to happen? Imagine, I'm going to simplify. Imagine that I have a map and then a filter and then a map. Let's imagine that, right? So three transformations, map, filter, map. This slot right here, CPU core, has this task to execute, which goes across three transformations. What it's going to do is take the first value, call map, call filter, and if filter says yes, call map. Then that creates an output. These two get thrown away immediately. These were just intermediate mathematical values. So it calls map, filter, map, and outputs this. Then it goes to this one, map, filter, map, outputs this. Throw these two away. Calls map, filter, map, throw these two away, and then keeps this. You see what's going on? I'm very quickly just chaining the calls across the three transformations, but on every value. map filter map as a single go right here, immediately throwing this away and preserving this. This is what happens. Do you see how super efficient this is? Because we don't have to actually create these RDDs. They don't get created. The values get created on the fly, but they don't actually get created. There is no need to send anything to other machines. You just, on the same machine, go all the way from here to here. Who sees that? Who is with me? Yeah, super efficient. That's what happens when there's no spaghetti. Okay. All right, and now that's called a stage in Spark, when you have multiple transformations, non-spaghetti-y, that you group together and you efficiently execute them with the same machines. This is called a stage. Now I said spaghetti, non-spaghetti-y. We have fancy names for that. Non-spaghetti-y, in fact, is called a narrow dependency. A narrow dependency means that every value in your output RDD only depends on one or very few values on the input RDDs. There's some notion of locality here. And if there is a narrow dependency, then this is how you can split it, right? And you can stay on the same machines. Yes?
One question from the Zoom. So what about the cross arrows of the previous slide? With this model, we are not able to keep them.
Look at it closer. Let's look at it. So this is the one that I said is inefficient. Do you see here that this is inefficient, right? But do you see here the chain that it goes like this? That even though here it was shipped on a separated in a different way, but it doesn't need to be. Imagine that these two, you bring them back here, right? It's just the same chain of mathematical calls, right? You see that? That's the thing to see in here. And then, of course, once you have done that and shifted this to here, then you realize you don't need these two machines. You can just keep the same machine, right? Does it make sense?
Yeah. Okay, thank you.
Yeah, so there is no spaghetti in there. I just put them a bit weirdly because it's not efficient, but if you look closer, there is still no spaghetti. Very good. So now I'm going to try to stop saying non-spaghetti-y, and instead I'm going to say a transformation with a narrow dependency or a transformation with a wide dependency, which is the spaghetti-y version. So if there's a narrow dependency, then I can stay on the same machine and I can split. And this is what I get. Now I have two transformations. I had 3 earlier, now it's 2. And you see that I have 2 transformations with 11 tasks on 2 cores. And now you see that in order to create the tasks, we just do it over multiple transformations, as long as they have narrow dependencies, right? I don't need to create tasks for every transformation, only for every stage. Okay. Something more is that you can control the number of executors that you want. In my case, there was 2 executors, but you can control that. You can tell the cluster, I have 42 executors. I want to have 42 executors. You can also specify the number of cores per executors. In my case, it was 2. So you say executor cores 2. And you can also control the amount of memory per executor. Just say 5G or 10M, you know, giga, mega, and so on. Tera works too with a T. So you can control number of executors, cores, memory. Now, when you do that, you need to sit down with a pocket calculator or or a sheet of paper and just make sure that it adds up. Because if you look at this, what does it mean? It means 42 executors with 2 cores each. So I need how many cores? 84, right? I need 84 cores. 42 executors with 3 gigabytes per executor means I need 126 gigabytes of memory. So you need to check that whatever cluster you're using has these resources, right? If you don't have a cluster with enough cores or enough memory, it's not going to create 42 of them. Maybe it's only going to create 20 of them, right? And the way to do that is really to, you book your cluster. Let's say you have, 6 machines. Then you're going to have 7 executors per machine, right? 7 executors per machine. So it means that per machine, you need 7 times 2, 14 cores per machine. So if the machines have 16 cores, then this is good. And 3 gigabytes times 7 per machine, that's 21 gigabytes per machine. Let's say you have 32 gigabytes per machine, then you're good, right? You just need to make sure that this matches your cluster configuration, right? Otherwise, it's going to not work as expected. But you can basically do the math and then put the commands in there. Now, spaghetti E, I told you, is called wide dependency, and that, of course, no longer works in the way that I've shown you, because what's going to happen here, we need to shuffle, right? There's shuffling in here, just like the shuffling on MapReduce. So this is when the shuffle actually happens. So now, whenever you saw a transformation with this, like distinct or intersection or join, like all of these need to shuffle, right? All right, and when you shuffle, then you have no choice. You will have to send the data over the networks, right? So in the most general case that you have plenty of transformation, so here I still have a linear order of transformation. It's not a generic tag. But let's say I have one transformation, then a shuffle. I have a wide dependency here. It's going to shuffle. Then I have a second stage, and immediately after that, I again have a wide dependency transformation. I have to shuffle again, and then I have a narrow dependency transformation right here that I can parallelize. But what's new is we might shuffle multiple times. That is the difference with MapReduce. In MapReduce, you just shuffle once, map, shuffle, reduce. Here, you will shuffle every single time there is a wide dependency transformation. That's roughly how it works. And whenever you're lucky that you have narrow dependencies, then you group them in stages and you don't need to shuffle, right? And so that means that concretely, if you trigger a job like that, then you have to visualize the entire cluster is going to be working on stage one, all carrying out the tasks and so on. When stage one is over, it shuffles. Then stage two begins, then it shuffles, then stage three begins, and so on, right? Every shuffling is blocking. Every time it shuffles, you cannot start the next stage until the former stage has completed. Just the same as in MapReduce, you cannot start reducing until you're done mapping. Okay. Who is with me? Good? Very good. And in general, of course, you might have generic DAGs, and you might have multiple stages and so on. Then you might have stage one first, and then stage two, and then stage three, and then stage four, right? So yeah, that's how it works. The join is heavily shuffling, right? The join is shuffling twice in a way. It's shuffling from the left, shuffling from the right, right? So that's expensive. Okay, now just a quick summary to remember the words. Transformations that have narrow dependencies get grouped in stages. The stages get physically split or chunked into tasks, right? And a sequence of stages gives you a job, right? Sequence of stages, which corresponds to a DAG of transformations and actions. So a job is just stage one, then stage two, then stage three, then stage four, and so on. Sequence of stages. Can be a bit intimidating at first, just because we have a mix of logical and physical, but that's how it works. Jobs are logical, transformations are logical, stages and tasks are physical, implementation details that the user doesn't see. So far, so good? Any questions? Not in the lecture hall on Zoom? Any questions? You can still interrupt me later. I can come back on some of the things later. Okay, so you saw the good news. What you've learned with MapReduce is actually useful because this idea of the tasks and slots works in exactly the same way. We can apply that to every stage. And the trick is to have a stage with multiple transformations with narrow dependencies, just for the sake of efficiency. Now we can tune a bit the performance. Now that will maybe also go back to the question that your colleague asked on Zoom earlier about the lazy evaluation. Look at this. This is a DAG of transformations. So of course, nothing happens yet because I didn't trigger any action. But let's see, I trigger an action here. I just take these RDT and say, okay, now I want to display them on my screen. Then this is going to force now the cluster to be set in motion and compute stuff, and then you will see on your screen the results. Now, imagine that the same person says, okay, I've seen the results on my screen. Now, let me use that RDD right here, and let's say collect it to a Python list. That's going to set in motion again the cluster, compute the transformation, and then you have your Python list. Then the same user says, now, I'd like to take that RDD and write it back to HDFS. So again, that's setting the whole cluster in motion and computing, and then it's going to write to HDFS. Do you see what's inefficient in here? What can be improved? On Zoom, maybe? Do you see it? Look at this again. I pull the trigger. I compute everything that's marked in orange gets computed. These are all RDDs, the rectangles. Then we compute again. Then we compute again. Do you see it now? What's inefficient? Exactly. We recompute the same thing all over again. Why don't we keep the results, right? And indeed, we can do that. It's like pinning the intermediate results. So what I can do, and that's the user who do that, the user can say, this RDD here is obviously important because all of these depend on it. So why don't I pin it? Like I say, okay, this one, keep it, don't throw it away. And then you see when I trigger my action, I don't need to recompute all of that because I already kept this one the first time, right? So this is called the persistence of RDDs. You can persist RDDs in memory, you can persist RDDs to disk, you can choose. And obviously, it's best effort because if you ask Spark to persist too many things and there's not enough memory, then Spark will not be able to persist everything, right? So there's a matter of priorities. If at some point you persist so many things that the memory is full, then maybe it's going to offload it to the disk, right, of the machines. Then it's just a bit slower, but still there. And if even the disk is becoming full, then it has no other choice than to throw it away, right? In that case, it will not be able to honor your request to persist it. Then it's just going to be slow. It's just going to recompute it, right? So you see the flexibility in there, right? If you ask to persist, it will do its best to persist it, as long as there is enough memory and enough disk to actually keep it. And if not, no big deal, you just recompute. That's why it's called resilient distributed data sets. Okay? Another trick that can be used to optimize is that in some cases, we can avoid shuffling. We can avoid shuffling if we have extra information. For example, imagine that I want to, let's say, group by key or reduce by key. And it turns out that somebody told me, or I have reasons or mathematical proofs that my input is already sorted, right? So somebody told me that this input RDD right there is already sorted. Who agrees that because it's already sorted, I don't need to shuffle in order to do my reduce by key? Do you see that? Because all the keys are together already, so you don't need to shuffle them. Right? Is that clear? Who gets that? So how could I know that? Maybe I would know that because I created that RDD right here, and that was the result of sorting, right? So if you have sorting followed by reduce by key, and the keys are the same as the sorting keys, then you don't need to shuffle, right? So it means that when you have wide dependencies, shuffling is not systematic. In general, you need to shuffle, but sometimes you don't need to. If you have this extra information that the keys are already where they're supposed to be and you don't need to shuffle again, right? And so, for example, you might have one side, let's say the right-hand side, it might be already sorted or the partitions were already made, maybe because of the way it was stored on disk or I don't know. Then in that case, for example, the join would only shuffle from the left, but not from the right. So this is the sort of optimizations you can actually do. It's already an advanced use of Spark to actually optimize in this way. but it can become very, very powerful when you start understanding what's going on with Spark. A good trick that the advanced users use with Spark is the so-called history server. Who has ever heard of that? So there's a secret code. Is it 4444 or 4040? It's one of the two, 4040 or 4444. You just need to, if you have Spark on your machine, connect to localhost 4040 in your browser. And if it's not 4040, it's 4444. I'm just not sure anymore. But basically, if you go there, you will have a super fancy website that contains all of the details of what's going on in the cluster. It will show you the stages and how many slots and how the tasks are with beautiful visuals of the execution of the tasks and so on. Super useful because then you can go there. It's like having a car and opening it and looking under the hoods to see what's happening. And that gives you a lot of insights to make your query much more efficient. Right. So, but then, of course, it's an advanced use of Spark when it goes in that direction. Any questions so far? Also not on Zoom? Okay. Who wants to continue? Right, okay. So you probably know this beautiful work of Ars that should actually have been called Data is in the Charts, that I think is very fitting for data frames that we are going to be looking at right now. That's an RDD, that could be a map RDD that is displayed right here with a function. And that's what it can look like. In that case, it's PySpark, right? That's the PySpark API where I read a file, that's a text file in that case. So I use the Spark context, the one that you so-called SC before if you're in the shell, dataset.txt. Then I filter the lines that contain Spark with this lambda function, right? Then I have a map that counts them. It's a bit like my Pokemons. And then I'm reducing with a plus. You know, that's my reduce function. It's just doing plus, 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 adding everything. And then I take the first 10 values in my RDD and collect them to a local Python list that I call results. So the first thing that you might notice here is that the code is not very easy to read, right? Who agrees with that? Right? And that's kind of what I want to convey to you, is that it works. There's APIs like Pandas, we're talking about it during the break, that allows you to do these kind of things, and Spark has a similar API with the transformation. We will see later that we can do better than that with query languages. That in fact exists, but it should be hidden. The users should not actually have to write things like this. But this was just text. What if it's JSON? And now you see it's even more complex because PySpark has no idea what JSON is. To Spark or regular Spark, JSON is just text, right? The JSON object can be serialized as text, so it only sees text. So it means that if you want to process JSON, you have to manually use a Python library or a Python method to actually read the line and parse it to a JSON object, which is then a Python dictionary, a Python dict with this, and then you have an RDD of Python dictionaries, right? Then you can filter them. And again, here, that has nothing to do with Spark. This is just the Python syntax to navigate in a Python dictionary, right? And then again, here, you're navigating in Python dictionaries and like this. So you see, it works, but it's not easy to write. It's the sort of things that you would actually rather ask ChatGPT to do it for you, right? Because it's a bit complex and not straightforward to write. But I want to tell you here is that it's not only that for the user, it's not convenient to actually have to handle JSON yourself. It's also that it's going to be inefficient because since Spark doesn't know it's JSON, it can also not optimize knowing it's JSON because it doesn't know. And of course, the Spark engineers, they're very clever and they figured it out that we can do better than that to handle use cases like this. And this is where data frames come into the picture. You might already have heard data frames several times. probably before the lecture if you've dealt with pandas and such libraries, but also you remember them from the validation lecture when I told you a data frame is basically a collection of valid JSON objects, right? If the schema has specific constraints. Do you remember that? It's the same data frames that I'm talking about right here. And so the idea is that data frames are actually RDDs, but they are specific RDDs. They are RDDs of records, RDDs of rows, if you want, if you see it as a table. Internally, you don't need to actually learn that, but in Java, that a data frame would be known as dataset row, but dataset row for marketing people is not good enough. You have to call it a data frame to sound a bit more appealing to the users, right? But if you see dataset row in Java, these are actually data frame. So the idea is that if you see a collection, an RDD of records, of table records, then your RDD is in fact logically a table, right? Your RDD is a relational table if your records are flat. Now, if you no longer require the records to be flat and homogeneous, then you get data frames in general, right? That can have nested structures and so on. So that's the idea of basically assuming that you don't have an RDD of whatever, you have an RDD of records. Or put otherwise, if you want to use JSON, we have an RDD of JSON objects that are valid against the same schema. That's how to visualize it. In fact, this one right here is an RDD of JSON objects. You agree? I parsed the JSON. These are Python dictionaries, JSON objects. So this is an RDD of JSON objects. And this is the one that I want to replace with a data frame, right? Because that's going to be more efficient. And the difference between just regular RDDs of Python dictionaries and an actual data frame is the storage. It's the way you will have it in memory. Because if you know that your RDD is made of JSON objects that have the same keys, they are valid against the same schema, then what you can do in your memory is that you can store the same keys together. So if you have JSON keys that have a key called first name, then in the memory, you will put all of the values that you have in your JSON objects together with the key first name. And then you might have another key birth date, and then you will put all of the values of each value in your RDD, each JSON object in your RDD will be stored in here. Logically, it's the same. It's an RDD of JSON objects, still the same thing. But in the memory, physically, you will have compressed all of the data, put all of the values that belong to the same keys together, and that is going to be massively more efficient. An example is, imagine you don't use these keys at all, these JSON keys. Then you can just drop it completely from the memory very early, right? You can optimize in a way you could not do if you just have regular RDDs of JSON objects. Who is with me? Right? So this is the secret. It's a physically, when you have a data frame instead of a regular RDD of JSON objects, then you can store in memory in this way. And the direct consequence is this is the memory you need compared to a regular RDD of JSON object. Turn it into a data frame, it shrinks in size, it's more efficient. That is exactly the same idea as Parquet that takes less size on disk than the original text of JSON. It's the same idea that we use data frames to compress collections of valid JSON objects, right? So connect that with the validation lecture when I explained that with Parquet. It's exactly the same thing. So the direct benefit is I need less memory and everything will just suddenly be magically faster. But there's something even better than that, is that because it looks like a table, and it is actually a relational table if the objects are flat and homogeneous. And who says table says SQL, right? So you remember the SQL brush up you did at the beginning of the semester? Well, you can put it right there with the SQL function right here, spark.sql. You just give a name to your data frame, call it dataset or whatever. You directly read it, right? You put your JSON file, you directly tell Spark it's a data frame, should be read as a data frame. Spark will automatically feed the schema, right? So if you do it, you probably assume there is some schema. Spark will figure it out. Automatic detection of the schema, calls it data set, and then you have a SQL query, good old SQL familiar, that magically computes the data frames. Below the scenes, it's going to be actually transformations and the same thing we've seen before, but much more efficiently and automatically. So now you see why it was actually worth revising your SQL. When I say automatic schema detection, this is what I mean. So in that case, that would be CSV. You can also read CSV, it doesn't have to be JSON. So imagine I have a CSV that I downloaded from the internet, from the Federal Office of Statistics or wherever. As a human, you probably see the schema in here, right? You see foo is an integer and bar is a Boolean, right? But Spark can also see that. And Spark is going to create a data frame with a colon foo that is an integer and a colon bar that is a Boolean. Automatic. Of course, the detection takes time. So if you had saved it as Parquet, then that would be even faster, because when Spark opens the Parquet file, it doesn't need to detect the schema. The schema is already in the Parquet file, right? So opening a Parquet file is even faster than detecting a schema for CSV or JSON. Who agrees here that's the same thing in JSON? Imagine that this is the JSON I'm reading. Spark will automatically detect the colon foo that is an integer and the colon bar that is a Boolean. It's magic, just works. Now, there are people who don't like SQL or who maybe love pandas. And these people, instead of using SQL, prefer to use a pandas-like API. That's totally fine. They can do that. And in fact, there is an API. It's not the same one as the one that I showed you earlier with RDDs. It's a different API that looks similar, but on data frames. And you can also write it like this. And that should feel similar to pandas. Who uses pandas? Has used it already? Some of you, right? So that should feel a bit similar. But of course, part of the message of a database lecture is that SQL is even easier and higher level than pandas. It doesn't mean it's useless. All it means is this here should be hidden. It exists, it's actually done, but it should be hidden from the user because it's much easier to learn a query language than it is to learn an API like this. API, I explained what it is, right? API is application programming interface. That's the generic name for when you have functions like this, when you have a Python library and you call the functions. All right. Now, it means that we have schemas, right? Data frames have schemas, and who says schema says types. So obviously, there's a type system in the data frames of Spark. I put them here. It's documented on the website. So you have, that shouldn't surprise you because we've spent 1 week studying schemas in a generic way. Surprise, surprise, we have atomic types, numbers, byte, short integer, long, float, double, decimal. We have strings, booleans, binary, timestamp, date. I expect that doesn't surprise you. It's always maybe a feeling of deja vu. We've covered that. And like any other type system, it has the good old same types. The names might be different, but this is how it is. And structure types, we have array, struct, and map. Array and struct correspond to JSON arrays and JSON objects. Map, I'm not going to say too much about it. It's a kind of object, but when the values have all the same type too. Right? That's basically, and the keys can be something else than strings. But let's keep the map aside. Focus on array and struct that correspond to JSON arrays, JSON objects. And I have yet another one of these beautiful type mappings that some of my students do in their projects when they map library to one another. So you have the beautiful correspondence here between Spark data frames in the first columns, Java types for whoever wants to use Java in the second column, Python types for whoever wants to use Python or PySpark in the third column, and JSONic, which is the higher level query language to which we are converging on the right. And you see different names, same types, right? Always the same idea here. All right, and the same goes, so here I told you array type would be a list in Java, a list in Python, basically an array. Map type, that's the one that is a bit different. That is neither a JSON array, neither a JSON object. Again, it's just a map from some keys to some values. So let's forget map type. Struct type, that is a JSON object, right? In Java, that would be called a row, but a row that is not always flat. A list in Python and an object in JSONic. Okay. So again, we have the mapping like this. Spark is able to read data frames from plenty of different places and formats. It can read, for example, from JSON and automatically infer the schema. It can read from Parquet. As I said, Parquet already contains the schema. That's the whole point of Parquet. So this is going to be super fast. Like Parquet is the fastest you can imagine to actually read data. That's why it's worth saving your data in Parquet before you start querying it. It can read from CSV. It can read from a text, in which case I assume it's probably going to create a data frame with one column of type string, and then one line of text is a value in that data frame. JDBC is a connector to relational database systems. So yes, absolutely, you can get Spark to connect to PostgreSQL, the same one we've seen in information systems for engineers that we've used in the SQL brush-up. So you can connect Spark to PostgreSQL. It will look at a PostgreSQL table as a data frame. Right? So that's really beautiful. And then you have also Avro, many other formats. JSON, Parquet, CSV text are a bit special because they are known already. And all others, you use format, blah, blah, blah. And that's anything that gets invented after Spark is opened in this way. Avro is just an example of that, but I haven't covered Avro in this lecture. All right. And the idea is that it's magic. The moment you have a data frame and you put a SQL query, Spark is going to automatically create the RDDs and the column representations in memory. It's automatically going to create the transformations that you need for your query. It's going to create what's called a logical plan, transformation of data frames, and then a physical plan, transformations of RDDs, but now it's all hidden. You don't even need to bother with RDDs anymore. It just takes care of everything for you. Right? So you see the beauty of data independence. And here, that's taken from the paper, that's everything that happens without you noticing when you use data frames. That all this cascade of detection, optimization, and so on that happens without you bothering. All you need to do is read a data frame from some file, put a SQL query, and all of that will happen automatically in the background, all the way to creating the RDDs for you. We'll have a few minutes. I'll probably finish on that slide. I want to say, you know SQL, it works like a Schweizerdeutsch, right? You have Baseldeutsch, Ostschweizerdeutsch, Berndeutsch, Zürichdeutsch, Luzerndeutsch, Walliserdeutsch, Embry, Embruf, and so on. It's the same with SQL. You have PostgreSQL, MySQL, and so on, all kinds of dialects. And you have, guess what, Spark SQL. That is another dialect. But I have two pieces of good news. The first piece of good news is that even though it's Spark SQL, it still looks like SQL. So it's the same. So select from where, group by, having, order by, limit, offset. This is new, by the way. It wasn't supported before, offset, but now in the newer versions of Spark, they also support offset. Second piece of good news, and I think that is Spark 4. I'm not sure, either 3.5 or 4, but I think it's 4. Spark has announced that they are increasing their compliance for SQL. So they have a mode in which the SQL is even more standard and closer to the standardized SQL as opposed to Spark SQL. So that's very good news when things move in the direction of a standard. So that you should be familiar with. And what you can do now concretely with Spark, take a JSON file or Parquet or CSV, write a SQL query like this, and it will just work, right? And now you know why it works, because I've explained the architecture and the tasks and the slots and so on. But this is what the final user is going to see. So I'm going to need to find the window. Yes, here it is. There you go. Just checking the speed. I asked in the middle of the course just to make sure, but I really want to make sure that I adapt my speed to you. So what I will do next week, I'll finish on that, but I will show you the limits of data frames, because it works until it doesn't work anymore. And you might have guessed that it stops working when there is too much nestedness, when you have too many tables in tables in tables, then the SQL queries become very complex. And the second thing is that if it's heterogeneous, then it doesn't really fit in a data frame anymore. And this is also where you hit the limits. And this is why we'll have document stores, and then we'll have JSONic, which address the limits of Spark SQL. And that will conclude the course, actually. This is our journey. All right, still have a majority above 80%. So there's no secret, actually. What is the best way to take it from there if maybe you didn't understand everything? Solve the exercises. Use Spark, go ahead, look at tutorials, use it, use it, use it, use it. I cannot encourage you enough to just use Spark. That's really the best way to learn it. Create JSON files, download data sets, write data frame queries, PySpark queries, and see the magic happen. And if you're less than half, that's totally okay. Write an email, ask your colleagues, write an email on the forum, or the Moodle forum, we are looking at it. Write an email to us, to the TAs, we can explain, right? And you can also ask your colleagues, because the best way to learn is to teach. So it's a win-win situation if you ask your colleagues, because the colleague who is going to explain it to you will also have an opportunity to strengthen their knowledge by explaining it. And I think that's pretty much it for today. Thank you very much, everybody. Enjoy the exercises and the quizzes. Thank you, Zubin, for moderating the lecture, and I'll see you next week at 8 a.m. for the continuation, probably document stores next week. See you, everybody. Thank you.